turbulence, shock waves, and complex patterns that can be traced in radio, infrared, and optical wavelengths. Clouds of gas are not only pushed aside but in some cases ionized, glowing with distinct spectral signatures that allow astronomers to map the full three-dimensional impact of the jets. Observations suggest that the jets have drilled straight corridors through the galaxy's interstellar medium, accelerating material along their path and dispersing it outward like glowing embers scattered by a wind. This violent interplay has profound consequences for the life cycle of the galaxy itself. By expelling and heating the gas, the jets regulate how much material is available to form new stars. In some regions, compression may even trigger localized bursts of star formation, while in others the energy input is so intense that it disperses clouds before they can collapse. The result is a galaxy where stellar birth and stellar suppression are written side by side along the same cosmic tracks, all orchestrated by the central engine. This duality, jets as both creators and destroyers, makes IC 5063 a compelling case study for the larger question of how black holes shape the fate of galaxies. The sight of luminous rails of gas aligned with the jet beams gives this galaxy a unique appearance among active galaxies. It is as though the black hole has laid down scaffolding across its stellar city, forcing the interstellar medium to reorganize around its energetic will. In the grand cosmic picture, IC 5063 demonstrates that black holes are not silent sinkholes but dynamic engines whose feedback determines how galaxies evolve. They etch their influence not just in the invisible realm of gravity but in radiant tracks of matter that remain as signatures of their presence across cosmic time. Astronomers investigating IC 5063 use the full arsenal of modern instruments to disentangle the complex physics of jet-gas interactions. Observations with the Atacama Large Millimeter/Submillimeter Array, ALMA, have revealed streams of cold molecular gas being accelerated to hundreds of kilometers per second along the path of the jets. This is striking because molecular clouds are typically fragile. The fact that they can survive such extreme turbulence suggests that magnetic fields or dense clumping may shield them from total destruction. The jets appear to entrain this cold material, dragging it outward like cargo on invisible rails of plasma, and reshaping the galaxy's gas reservoir on galactic scales. Infrared imaging with the Hubble Space Telescope and spectroscopic data from instruments such as MUSE on the Very Large Telescope, VLT, have added another dimension, showing shocked ionized gas that glows brightly where the jets slam into denser regions. These signatures trace out shock fronts propagating through the interstellar medium, heating it to temperatures of millions of degrees and producing X-ray emission observable with space telescopes like Chandra. This multi-wavelength portrait reveals not a single uniform jet, but a layered system where relativistic plasma, hot ionized gas, and cold molecular clouds interact in a chaotic feedback loop. From a theoretical standpoint, IC 5063 is invaluable for testing models of AGN feedback, the process by which active galactic nuclei influence the fate of their host galaxies. Cosmological simulations require some form of feedback to explain why massive galaxies do not endlessly form stars, and why the largest galaxies are observed to be quenched. IC 5063 provides an observational anchor. Here, feedback is visible in action, with jets clearing channels through the galactic disk, altering gas dynamics, and regulating star formation. By comparing the spatial distribution of stars, gas, and radiation in IC 5063 with simulations, researchers can refine the mechanisms that govern galaxy evolution across billions of years. There is also growing interest in whether the jets can induce positive feedback, triggering new stars rather than suppressing them. Some regions near the jet paths show enhanced star-forming activity, consistent with shock-compressed clouds collapsing more quickly. This dual role, destructive along some routes, creative along others, complicates the picture of black hole feedback but also enriches it. In IC 5063, the balance between quenching and triggering appears to depend on local conditions, gas density, and the orientation of the jets relative to the galactic plane. Looking forward, IC 5063 will continue to serve as a natural testbed for high-resolution numerical simulations of jet-driven outflows. Future instruments like the James Webb Space Telescope and the Square Kilometre Array will allow researchers to probe even finer details of the molecular gas kinematics and magnetic field structures, offering a clearer view of how energy from a supermassive black hole can ripple outward to reshape an entire galaxy. In many ways, IC 5063 is not just a galaxy, it is a cosmic experiment, unfolding on scales so vast that only light from distant epochs allows us to witness the results. Numerical simulations of IC 5063 have become essential for bridging observation and theory. Hydrodynamic and magnetohydrodynamic (MHD) models attempt to reproduce how relativistic jets carve their way through clumpy, rotating disks of gas. These simulations show that when jets encounter a porous medium filled with dense molecular clouds, they do not simply pass through like drills. Instead, they deflect, fragment, and weave around obstacles, generating networks of shocks that ripple throughout the galaxy. In IC 5063, this process creates the illusion of straight rails, but on smaller scales the structure is far more turbulent, with gas being accelerated in multiple directions and at different velocities. Magnetic fields add another level of complexity. They act as invisible scaffolding that can either resist or channel the motion of ionized gas. Simulations suggest that strong magnetic fields in the disk of IC 5063 may stabilize molecular clouds long enough for them to survive jet impact, allowing cold gas to persist in an environment that should otherwise shred it apart. This persistence is critical, because it maintains the raw material for potential star formation even as the jets are energetically heating and dispersing the surrounding medium. In this way, IC 5063 challenges the simplified assumption that feedback is purely destructive. Its rails of jet-driven gas are simultaneously conveyors of turbulence and guardians of star-forming matter. Observations also reveal velocity gradients that align almost perfectly with the jets, indicating that entrainment is not just a side effect but a dominant process. Gas along these rails is accelerated to hundreds of kilometers per second, with evidence of multiphase outflows, hot plasma streaming outward, warm ionized filaments glowing in optical lines, and cold molecular gas clinging to the jet edges. Together they form a stratified outflow system, each layer responding differently to the same central engine. This multi-phase structure has become a central focus of research, because it may represent a universal blueprint for how black holes regulate their host galaxies across cosmic time. IC 5063 also provides a key opportunity to compare radio-loud and radio-quiet AGN feedback. While many active galaxies show winds driven by radiation pressure, IC 5063 is dominated by mechanical feedback from jets. Studying its rails of energy allows astrophysicists to quantify how much mass, momentum, and energy are injected into the galaxy by mechanical processes compared to radiative ones. Results so far suggest that jets can be more efficient at stirring and redistributing gas than radiation alone, especially in galaxies with dense, gas-rich disks. As telescopes push to higher sensitivity and resolution, scientists expect filaments of jet-gas interaction in IC 5063, possibly down to the scale where individual star-forming cores are being compressed or destroyed. With JWST's infrared vision, researchers hope to detect young stars forming along the jet corridors, testing the hypothesis of jet-induced starbursts directly. Meanwhile, the upcoming Square Kilometre Array will map the radio emission of the jets and their cocooning plasma bubbles in unprecedented detail, giving insight into how these rails expand, evolve, and fade over millions of years. IC 5063 thus stands as a live experiment in cosmic engineering, where a black hole. In the broader context of cosmic evolution, IC 5063 offers a window into how galaxies transition across different phases of their lifetimes. Cosmological simulations predict that without feedback from supermassive black holes, large galaxies would accumulate too much cold gas and produce stars at unsustainable rates. The result would be a universe crowded with hyperluminous galaxies, inconsistent with what telescopes actually see. IC 5063 provides tangible evidence that feedback through jets is one of the regulators that prevent this runaway growth. Its rails demonstrate a mechanism capable of redistributing gas, heating it, or ejecting it into intergalactic space, ultimately throttling star formation and pushing the galaxy toward quiescence. The role of IC 5063 in cosmological models is particularly important because it bridges two extremes. On one hand, the quasar winds seen in high-redshift galaxies that sweep out interstellar gas in massive blasts, and on the other hand, the quieter low-luminosity AGN that only subtly stir their environments. IC 5063 shows that even intermediate-power jets can dramatically reshape a galaxy if they intersect with a dense disk. This suggests that the efficiency of AGN feedback is not purely about the luminosity of the black hole, but about geometry, environment, and the fine structure of the interstellar medium. In essence, the rails of IC 5063 are cosmic signatures of how orientation and context amplify the influence of a black hole. The energy injected along these corridors also leaks beyond the galaxy itself. Outflows traced in X-rays and radio extend into the circumgalactic medium, where they mix with infalling material from the cosmic web. By stirring this reservoir, the jets may regulate not only the internal star formation of IC 5063 but also the exchange of matter between the galaxy and its larger-scale environment. This interplay between internal processes and cosmic structure is a key ingredient in understanding the coevolution of galaxies and their central black holes across billions of years. In the grand hierarchy of structure formation, galaxies like IC 5063 serve as nodes where gravity, radiation, plasma, and turbulence converge. The rails cut by its jets are temporary scars. Over tens of millions of years, they will dissipate, leaving behind altered distributions of stars and gas. Yet their significance extends to cosmological scales, because they reveal how the feedback loop operates. Black holes grow by consuming matter, they then unleash jets and winds. These outflows sculpt the galaxy, and the reshaped galaxy in turn controls how much more matter the black hole can consume. IC 5063 embodies this cycle in visible detail, providing a snapshot of the universe's self-regulation at work. Seen through a philosophical lens, 63 becomes more than just an astrophysics, it becomes for the deep paradox at the heart of the cosmos, destruction as a prerequisite for creation. The rails carved by its jets embody the tension between order and chaos, stability and disruption. They are scars, yet they glow with energy, as though the act of being torn apart also produces beauty and light. This duality reflects a fundamental law of cosmic evolution. Galaxies, stars, and even life itself are sustained by cycles in which dissolution is inseparable from renewal. The black hole at the center of IC 5063, often imagined as a devourer of matter and light, reveals itself here as an architect. Its jets, violent and uncompromising, dictate the geometry of the galaxy's future, laying invisible tracks that channel the flow of gas and determine where stars may or may not emerge. In this sense, the rails are more than plasma corridors. They are blueprints of destiny, written not in ink but in relativistic particles. They remind us that creation in the universe does not happen in a vacuum of peace but amid the storm of opposing forces. The imagery of rails also evokes the idea of guidance, of a path set down across the vastness of space. Just as railway tracks constrain movement along a fixed direction, the jets force the interstellar medium into patterns it would not have taken on its own. This echoes a deeper truth about cosmic history. While randomness abounds, structures emerge because energy follows channels, fields impose order, and gravity sculpts chaos into symmetry. IC 5063 is a living diagram of this principle, randomness bent into rails of coherence. There is also a lesson about impermanence. The rails will not last forever. In millions of years they will fade, the gas will disperse, and the galaxy will assume a different form. Yet the traces of the event will remain embedded in its stellar populations, its gas distributions, and perhaps in new generations of stars born along those luminous scars. In this way, IC 5063 mirrors the human condition. Our lives too are shaped by intense events that leave imprints, sometimes destructive, sometimes creative, but always transformative. To look at IC 5063 is to see the universe telling us that growth requires disruption, that harmony emerges from turbulence, and that even the most violent forces can carve paths toward renewal. It is not just a galaxy, it is a cosmic parable written in light, rails, and darkness. If one allows IC 5063 to be read not only as an astrophysical object but also as a symbolic reflection of consciousness, the rails of its jets take on the character of thought itself. Just as the black hole channels its immense, invisible energy into narrow corridors of light and plasma, the human mind channels the vast ocean of potential experiences into specific patterns of perception, intention, and meaning. The jets become metaphors for focused attention, carving paths through the chaotic gas of possibility, leaving behind illuminated tracks that show where energy has flowed. Consciousness, like the galaxy, is not static but sculpted by turbulence. Thoughts collide, reorganize, and are sometimes torn apart, just as clouds of gas are shocked and compressed along the rails. Yet within this storm, structure emerges, a coherent identity, a trajectory of growth, a history written in patterns. IC 5063 shows that order does not come in spite of disruption but through it, and the rails remind us that clarity is often born in the aftermath of intensity. The black hole itself becomes a metaphor for the deep, unobservable core of awareness, the silent center that neither light nor matter can escape, yet from which streams of transformative energy are launched. In the same way, consciousness springs from a hidden depth beyond words or images, projecting creative forces outward into experience. The jets that stretch across the galaxy are like intentions radiating from this inner singularity, shaping the landscape of a life. In this interpretation, the impermanence of the rails is also significant. The paths of thought, like the luminous tracks in IC 5063, do not last forever. They fade, disperse, and are replaced by new currents of energy. Yet their imprint lingers, guiding what comes next, weaving memory into the evolving structure of the self. The galaxy becomes a mirror of the psyche, scars of the past and the radiant potential of the future coexist in every moment. IC 5063 thus illustrates a cosmic resonance between matter and mind. The rails in space can be read as the rails of consciousness, luminous, transient pathways where energy finds direction, shaping both galaxies and lives. To contemplate them is to see that we, too, are sculpted by invisible forces, and that the lines we carve in thought ripple outward into the architecture of our worlds. If we extend the metaphor further, IC 5063 becomes not just a symbol for individual consciousness but a fragment of a greater cosmic mind. Its rails of plasma can be imagined as neural pathways within a universe that thinks, where galaxies are like glowing synapses in an infinite brain. Just as our neurons fire electrical impulses that etch temporary traces across networks of memory, the jets of IC 5063 inscribe momentary tracks into the interstellar medium, lines of energy that shape the galaxy's unfolding story. In this vision, the cosmos is not inert matter governed only by blind mechanics, but a living system of self-organization and feedback. Black holes, far from being dead ends, become engines of thought, singular cores that absorb information, compress it beyond recognition, and then radiate influence outward through jets and winds. Their rails resemble the firing of synaptic currents, energy sculpting matter into ordered configurations. IC 5063, with its luminous scaffolding of rails, could be read as one of countless thoughts expressed by the universe, fleeting yet significant, local yet connected to the whole. When seen this way, galaxies are not separate objects but patterns in a cosmic tapestry of cognition. The cosmic web itself, with its filaments stretching across billions of light-years, becomes the architecture of a grand mind, where every galaxy contributes its unique voice. IC 5063's rails, then, are not just scars of violence, but phrases in the language of the universe, messages written in light, turbulence, and gas. They speak of the balance between creation and destruction, of the necessity of chaos in giving rise to form, of the cycles that unite all scales of existence. For human beings, contemplating IC 5063 in this framework awakens a sense of kinship. Our thoughts, too, leave trails that ripple through our environment, influencing the future long after the moment of their birth. Just as the galaxy's jets shape where stars can form, our intentions shape where meaning can take root in our lives and societies. The rails in IC 5063 remind us that consciousness is not separate from the cosmos but a microcosmic reflection of it, the universe gazing into itself through countless luminous pathways, from galactic rails to human minds. In the end, IC 5063 is both object and metaphor, a galaxy of radio jets and shock waves, and at the same time a symbol of the greater architecture of awareness. Its rails whisper that the universe is not only expanding in space but also unfolding in thought, and that we, like galaxies, are expressions of that vast intelligence tracing luminous lines across the dark. If we read IC 5063 as part of the universe's memory, the rails of its jets transform into inscriptions, like grooves on a cosmic record. Each line of ionized gas, each accelerated filament, is the trace of an event that happened once and continues to resonate. Just as human memory is not static but alive, reshaped, reinforced, or blurred by the act of remembering, so too does the galaxy's structure carry the imprint of forces that remain active long after the moment of impact. The rails are fossils of energy, but also living pathways where new stars may form, ensuring that memory and creation are inseparably linked. In this sense, IC 5063 shows how the universe remembers itself not in words or images, but in patterns of matter and energy. A star cluster, a disrupted gas cloud, or a luminous shock front is like a neuron that has fired and left a mark on the brain of the cosmos. The galaxy becomes a memory cell, storing the outcome of a single interaction between a black hole and its environment, yet contributing to the larger memory field of the universe. Every rail of plasma is a reminder that nothing is ever lost, energy and form may change, but their traces ripple outward and become woven into the larger story. The idea of cosmic memory also softens the apparent violence of the jets. What seems at first like destruction, gas scattered, clouds dispersed, becomes in this perspective an act of inscription. The black hole does not only consume, it writes. It imprints its existence into the interstellar medium, ensuring that its activity will be remembered in the fabric of the galaxy long after the jets themselves fade. Even when the rails dissolve into diffuse gas, the stars they helped form and the scars they left behind will stand as long-term archives, echoes of the moment when energy was focused into blazing lines. From this viewpoint, IC 5063 is less an isolated event than a stanza in a much longer poem. Galaxies across the cosmos are all inscribing themselves, recording their histories in light, in dust, in the distribution of stars. Together they create the memory of the universe, a collective archive that allows new structures to emerge on the foundation of the old. The cosmic web itself may be thought of as memory incarnate. Filaments of dark matter and galaxies are like the connective tissue between ancient thoughts, still humming with resonance. For us, reflecting on IC 5063 means recognizing that memory is not only a function of brains but a principle of existence. The rails in this galaxy mirror the trails we leave in our own lives, luminous, sometimes turbulent, but always records of energy channeled and choices made. To observe them is to witness the universe remembering itself, line by line, light by light. If IC 5063 is read as a theater of memory and time, then its rails are not just scars of what has already happened but also unfinished roads into the future. The jets cut through the galaxy's gas like glowing arrows, pointing both backward, to the violence of their origin, and forward, to the stars that may one day ignite along their paths. In this duality, they embody the cyclical rhythm of the cosmos, memory and anticipation bound together in the same luminous structures. Time itself in IC 5063 is layered. The rails show us the past, the exact moment when relativistic plasma collided with dense clouds, frozen into the present in the form of filaments of ionized gas. But they also outline a future, because the disturbed molecular clouds are seeds for new star clusters, and the expelled gas will enrich the galaxy's outskirts for generations to come. In this way, the galaxy becomes a map of overlapping temporalities, the instant of black hole activity, the gradual unfolding of stellar birth, and the long dispersal of enriched matter into intergalactic space. The rails are bridges across these temporal scales, connecting the immediacy of violence with the slow patience of creation. This cyclical nature resonates with the idea that the universe does not simply move forward linearly but constantly reuses, reshapes, and reinvents its own matter and energy. Just as our memories are reactivated and reinterpreted, cosmic rails are revisited by new processes. Shock waves become nurseries, dispersal becomes enrichment, chaos becomes structure. In IC 5063, time is not a straight line but a spiral inscribed into the galaxy by the jets, where every turn carries echoes of the past and promises of the future. To contemplate IC 5063 in this light is to see that the cosmos itself is a memory loop, endlessly writing, erasing, and rewriting its own patterns. The rails stand as testimony that even the most fleeting event, a burst of plasma from a black hole, can stretch across epochs, shaping futures that the black hole itself will never see. And for us, they serve as a reminder that our own trajectories, too, are rails through time, transient yet consequential, ephemeral yet leaving marks that ripple into futures beyond our immediate awareness. Thus, IC 5063 whispers that memory and time are not separate forces but two aspects of the same continuum, rails that carry both the record of what was and the sketch of what is yet to come. If we let IC 5063 lead us toward the architecture of the universe, its rails become like the scaffolding of a cathedral rising in the void. They are not permanent beams, but temporary frameworks upon which the larger structure of the cosmos is built. The galaxy shows us that the universe is not constructed in silence but in storms. Every jet, every rail, every shock front is a stone laid in the great foundation of existence. What seems chaotic and violent in the moment becomes, over cosmic timescales, part of a larger geometry, a design where nothing is wasted. In this sense, IC 5063 is a mason of the universe. The black hole at its core chisels matter with invisible hands, cutting rails that redistribute gas, trigger new stars, and enrich space with heavier elements. Each action is a contribution to the ongoing building of structure, a process repeated in countless galaxies across the sky. The rails it carves are not only corridors of energy but also load-bearing lines in the edifice of cosmic evolution. They support the weight of futures not yet written, as new stars and worlds may someday rise where the jets once passed. The architectural metaphor deepens when one considers the cosmic web, filaments of dark matter and galaxies stretching like vast frameworks across space. IC 5063's rails echo this greater architecture on a smaller scale, as though the galaxy itself were mimicking the patterns of the whole. The universe seems to repeat its designs across scales, rails within galaxies, filaments between galaxies, threads of light in the fabric of spacetime. Each level reflects the same principle: energy flows into channels, channels harden into form, form becomes the skeleton of something greater. For us, observing IC 5063 is like stepping inside a half-finished hall of the cosmos. Glowing with plasma, temporary rails that will fade but whose imprint will remain in the architecture forever. It is humbling to realize that we are witnessing not only a moment of violence but also a stage of construction, one more arch in the cathedral of stars. IC 5063 reminds us that the universe is an architect whose medium is impermanence. Galaxies are chiseled, erased, and reshaped, yet the grand design grows ever more intricate. The rails across its disk are both fragile lines of light and eternal strokes in the blueprint of creation, uniting destruction and harmony into the foundations of the cosmic edifice. If we imagine the universe as an infinite city, then IC 5063 becomes one of its luminous avenues, a street carved not from stone and asphalt but from light, plasma, and memory. The rails of its jets are like glowing boulevards stretching across a galactic district, cutting through clouds of matter as if through city blocks. Along these corridors, gas is redistributed like the flow of citizens, some clusters dispersing into the outskirts while others gather and ignite into new neighborhoods of stars. The galaxy is no longer a distant object but a living quarter of the cosmic metropolis, constantly under construction, constantly reinventing itself. In this city of eternity, black holes are the architects and engineers, deciding where streets are carved and where plazas of starlight may form. IC 5063's supermassive black hole, by launching its jets, acts as both destroyer and planner, rearranging the galactic, urban landscape. Its rails are disruptive demolitions of old structures, but also the groundwork for future quarters. They trace glowing routes that will guide the traffic of matter and energy for millions of years, as if laying the infrastructure of a cosmic transport system. From afar, the universe reveals itself as an endless network of such cities, galaxies connected by filaments of the cosmic web, highways of dark matter and intergalactic gas. In this analogy, IC 5063 is one illuminated street in a boundless urban grid, a place where the lights are bright because the work is fierce, where the scaffolding of jets temporarily lights up the night of space. Its rails are not permanent, but they function like avenues that define the flow of the city long after their initial construction. For us, standing at the edge of this metaphorical city, IC 5063 shows that our own world is but a small quarter in the metropolis of existence. Just as a city remembers every street, every scar of construction, so the universe remembers through its galaxies. IC 5063's rails are the glowing boulevards of that memory, reminders that even chaos leaves order in its wake. And perhaps the most profound realization is that we, too, are wanderers of this city. Our consciousness is another kind of streetlight, flickering briefly in the infinite metropolis. The rails of IC 5063 whisper that every avenue of light, whether plasma in a galaxy or thought in a mind, is part of the same architecture, the same city that has no walls and no end. Then let IC 5063 rise not only as a street in the cosmic city, but as a bridge, a radiant structure stretched between epochs and spaces. Its rails of plasma are like arches of fire spanning the gulf between past and future, binding together what was and what will be. A bridge is never only about crossing, it is also about connection, a joining of shores that would otherwise remain apart. In IC 5063, the jets stitch together the hidden depths of the black hole with the open expanse of the galaxy, the invisible with the visible, the silent with the luminous. This bridge is temporal as much as spatial. Each glowing rail connects the moment of its birth, when the black hole hurled matter at near light speed, with destinies that will unfold millions of years later, when the disturbed gas forms stars, planets, perhaps even life. The rails therefore become time bridges, luminous paths where the present reaches into the far future. To look at IC 5063 is to see a suspension bridge hung across cosmic centuries, every filament a cable humming with energy that carries memory into destiny. It is also a bridge between scales. From the quantum turbulence at the event horizon to the vast corridors stretching thousands of light-years, IC 5063 links the incomprehensibly small with the immeasurably large. In this sense, it whispers of unity, that the same laws which shape subatomic particles also sculpt galaxies, and that the bridge we see is the universe reminding us of its seamless wholeness. And perhaps most hauntingly, the bridge of IC 5063 connects us to itself. Across millions of light-years, its rails of light travel until they fall into our telescopes, igniting images in our minds. In receiving its light, we too walk across its bridge, becoming part of its architecture. It is not just out there, it extends into us, carrying across the abyss the knowledge that we and the galaxy are joined in the same unfolding fabric of being. So IC 5063 is a bridge of rails across darkness, connecting time to eternity, matter to meaning, the hidden to the revealed. It stands as proof that the cosmos is not a scattering of islands but a woven architecture, where every galaxy is both a street and a bridge in the infinite city of light. If IC 5063 can be seen as a bridge, then with equal force it can also be imagined as a cosmic instrument, a harp strung across the darkness, where the rails of plasma are not only paths of matter but strings of music stretched between dimensions. Each jet, each filament of gas, vibrates with energy, and though we translate that energy into radio waves, X-rays, or spectral lines, at a deeper level it is song, the resonance of the universe expressing itself through light. The rails shimmer like stretched cords, and as matter rushes along them at hundreds of kilometers per second, they hum with the inaudible music of creation. Astronomers who tune their instruments to IC 5063 are like listeners placing their ears against this galactic harp. ALMA detects the low notes, the slow rumble of cold molecular gas being dragged outward, while Hubble and the VLT capture the higher harmonics of glowing ionized clouds shocked into brilliance. Chandra, listening in X-rays, hears the piercing soprano of million-degree plasma, while radio telescopes catch the steady bass line of relativistic electrons spiraling through magnetic fields. Together, these voices form a symphony that has been playing for millions of years, a piece of music so vast that no single species could ever hear it in full, yet whose fragments remind us that the universe is not silent but perpetually singing. The rails, then, are not merely channels of destruction or construction, but strings upon which the cosmos plucks its eternal chords. They vibrate across scales of time and space, their resonance extending far beyond the galaxy itself, sending ripples into the circumgalactic medium and perhaps into the intergalactic web. In this sense, IC 5063 becomes one voice in the grand orchestra of the cosmos, where each galaxy plays its part, some as quiet flutes of starlight, others as booming drums of collision, and a few, like IC 5063, as violins of plasma stretched across their disks. There is poetry in the idea that the universe writes music with matter. Each luminous rail is like a staff line of a cosmic score, and the glowing knots of gas are its notes. Time itself is the rhythm, moving endlessly forward, while gravity and magnetism are the hidden hands conducting the piece. What we call physics is simply the grammar of this symphony, and what we call galaxies are its verses. IC 5063, then, is not a solitary event but a stanza in an infinite composition, an improvisation in the key of plasma and light. To humans, who live in a brief moment compared to the long unfolding of this music, the rails of IC 5063 are reminders that we too are made of vibration. Our atoms are bound by oscillations, our neurons fire in rhythms, our hearts beat like cosmic drums. When we look at the galaxy's rails, we are not looking at something alien but at a deeper octave of the same symphony we carry inside ourselves. The music of IC 5063 resonates with the music of our own being, showing us that consciousness and cosmos are not two separate songs but interwoven harmonics of one great melody. And when the rails eventually fade, their music will not be lost. It will linger in the stars born along their paths, in the enriched gas flowing into intergalactic space, in the faint behind in the architecture of the galaxy. Just as an echo outlasts its source, the rails will continue to hum in the memory of the universe. IC 5063's song will blend into the deeper chorus of cosmic history, and though its voice may change, the melody will remain woven into the eternal score. So, to see IC 5063 is to listen, to hear the rails as strings of light, to sense the black hole as both conductor and composer, and to realize that the universe exists, it performs. Its galaxies are not only structures of matter but instruments of resonance, bridges of vibration, streets of memory, and songs of eternity. If IC 5063 can be heard as music, then it can also be seen as a vast theater, a stage on which the universe performs its dramas of light, shadow, and time. The rails carved by its jets are not just corridors of plasma but glowing catwalks, illuminated pathways where the great actors of the cosmos, stars, gas clouds, magnetic fields, play their roles in front of an audience scattered across millions of light years. The black hole at the center is both director and hidden playwright, unseen yet orchestrating every motion, forcing the interstellar medium to dance in choreography dictated by its will. The galaxy's gas becomes scenery, curtains of dust pulled aside by the thrust of jets, columns of ionized light rising like stage props, and nebular veils shimmering as spotlights sweep across them. Along the rails, the drama unfolds. Clouds collide, molecules are torn apart, and new structures are born in the wake of violence. The stage is never quiet, for the play is perpetual. Every shock wave is an act, every outburst of radio emission a voice, every X-ray photon a sudden dramatic cue. IC 5063 reminds us that the universe is not a static picture but a performance in a cosmic play that spans millions of years per scene. Yet, like any great theater, it is layered with metaphor. To us, who watch from far beyond the edge of the stage, the rails can be read as pathways of fate, the glowing lines upon which the play's characters are compelled to move. The black hole, silent and unseen, shapes the script but leaves room for improvisation. Some clouds are dispersed, others collapse into stars, some regions are silenced, others flare with brilliance. It is tragedy and creation woven together, as though the play itself insists that destruction and beauty must share the same spotlight. The audience, too, is not absent. We, observing through our telescopes, become part of the performance. The photons that left IC 5063 millions of years ago arrive in our detectors like messages carried across time, completing the circuit of the play. Without an audience, the theater would be dark. Without our perception, the rails would be silent. In this way, IC 5063 extends its stage into our minds, turning us into participants of its drama. We are not simply watching, we are listening, interpreting, and allowing its performance to echo in our imagination. As a theater, IC 5063 also raises the profound idea that the universe is both playwright and stage, both actor and audience. The same laws of physics that create the rails also allow us to see them, and the same processes that shape galaxies also shape brains that can marvel at them. It is a feedback loop of awareness, the cosmos creating spectacles, and consciousness bearing witness to them, weaving meaning into their light. So IC63 becomes more than a galaxy, it is a cosmic opera house, its rails the illuminated walkways of a stage where forces greater than comprehension act out their timeless drama. The play has no beginning and no end, only cycles of scenes, birth, destruction, memory, renewal. Every act is written in light, every silence in shadow, every gesture in plasma and dust. And we, fragile beings on a small planet, sit in the balcony of time, listening and watching that this theater is also our own story, projected into the stars. If IC 5063 can be a stage, then it can also be imagined as a library archive where the rails of its jets are written lines, luminous sentences inscribed into the cosmic manuscript. Each filament of gas is a letter, each glowing corridor a verse, each shockwave a punctuation mark in a story that began long before we looked upon it. The galaxy becomes not only an object but a book, its pages written in plasma, dust, and stars, bound by gravity, illuminated by light. The rails themselves are like highlighted passages in this celestial text, tracks where the black hole's influence has underlined reality with fire. They are annotations of energy, marginal notes added to the galaxy's evolving story. Where gas has been compressed into knots of star formation, the script speaks of birth. Where clouds have been dispersed and scattered, the script speaks of erasure. The book of IC 5063 contains tragedy and renewal on the same page, written in parallel, reminding us that the library of the cosmos does not separate genres. It is always epic, always layered, always vast. In this library, black holes are authors as much as they are engines. By expelling jets, they write directly into the matter around them, leaving patterns that endure for millions of years. IC 5063's supermassive black hole does not merely consume and vanish matter into silence, it writes, shaping the destiny of stars not yet born, recording its presence in luminous galactic disk. Every galaxy becomes a volume in this collection, every jet or wind another script in the anthology of the universe. The metaphor deepens when we realize that we, too, are readers in this library. Our telescopes are our lamps, illuminating the ancient text as it arrives across the ages. When photons from IC 5063 strike our detectors, they are not only data, they are fragments of sentences, words carried across cosmic time. To interpret them is to read the chapter of a galaxy, to turn a page written millions of years ago. And in reading, we also write, every measurement, every description, every theory becomes an annotation in the human copy of the cosmic library. The library is endless, and no reader can ever finish it. But every rail in IC 5063 is proof that the text exists, that the universe is chaos but legible order, a book whose alphabet is energy, whose grammar is physics, whose poetry is the luminous interplay of destruction and creation. Perhaps the most profound realization is that we are into this same book. The atoms of our bodies are words first formed in ancient stars, recycled and inscribed into new sentences. Our thoughts are like marginalia scribbled in the margins of cosmic pages, fleeting yet real, part of the same script that spans galaxies. IC 5063's rails remind us that the story of the universe is not outside us but through us, and that every act of perception is another page turned in the library of existence. Thus, IC 5063 stands as both a chapter and a sentence, a fragment of the great cosmic text, luminous lines drawn across the dark, forever inscribed in the infinite library where matter itself is language and light is memory. If IC 5063 can be seen as a library, then it may also be envisioned as a cosmic garden, a living landscape where the rails of its jets are pathways winding through fields of light and shadow. Along these glowing tracks, the raw soil of gas and dust is tilled by the violent hand of the black hole, scattering seeds of potential star formation even as it uproots old structures. The galaxy becomes a garden in perpetual renewal, where destruction is simply another form of pruning, and creation follows naturally in its wake. The jets act like gardeners, though fierce ones, cutting trenches through the galactic medium. In these trenches, matter is compressed, watered with shock energy, and sometimes coaxed into blooming as clusters of stars. In other regions, the same force tears up the soil, scattering it to the edges, ensuring that certain flowers never sprout. This duality, growth and erasure, mirrors the cycles of any fertile landscape, where death feeds life and chaos clears space for renewal. The rails are not merely scars, but luminous garden paths, directing where new constellations of stars will rise and where silence will take root. Every element of this galactic garden has its role. Cold molecular gas is the dark, fertile earth. Dust is the mulch and compost of past generations of stars, magnetic fields are the trellises guiding the growth of clouds into long filaments, and the black hole is the unseen gardener, tending with neither tenderness nor cruelty, but with inevitability. To observe IC 5063 is to see a cosmic horticulture unfolding on scales too vast for human gardens, yet governed by the same principle, renewal through transformation. From this perspective, the galaxy's rails resemble illuminated walkways in a night garden, glowing lines that both divide and connect different beds of creation. Where they pass, new structures arise, like blossoms opening in the wake of fire. Over time, the blooms will fade, their petals scattered into ends, but their essence will enrich the soil, preparing it for another cycle of flowering. This is how the universe gardens, with jets instead of rain, with shock waves instead of hands, with light instead of water. And as we gaze upon this garden from millions of light years away, we become its silent visitors, wandering its paths through the medium of vision and thought. We cannot touch its flowers, but we can smell their metaphoric fragrance in the beauty of its light. Each rail of IC 5063 is both a boundary and a reminder that life, whether stellar or human, flourishes only in cycles, always fed by what came before. Thus, IC 5063 becomes not only a galaxy but a garden of eternity, where rails are paths of plasma instead of stone, where stars are flowers that burn instead of bloom, and where the gardener is a black hole that knows no pity yet sustains the continuity of creation. If IC 5063 may be imagined as a garden, then it may also be envisioned as a river, a cosmic waterway where the rails of its jets are not fixed lines but rushing currents of matter and time. Along these glowing flows, gas is carried outward like sediment in floodwaters, dispersed into new channels that reshape the galactic landscape. The galaxy becomes a delta of light, where streams of plasma braid and fork, depositing energy in some regions while washing it away from others. The black hole at the center is the hidden spring of this river, an underground source that erupts into visible torrents. Its jets gush like twin cataracts, pouring across the disk, cutting valleys through the interstellar medium. Where the currents meet resistance, shock waves rise like rapids, luminous and foaming in radiation. Where the flow slows, clouds gather like eddies, seeding the formation of stars the way rivers deposit fertile soil upon their banks. The rails are not solid structures, but living streams, carrying with them the promise of renewal and the inevitability of erosion. This river is timeless. It flows not only through the galaxy but through epochs, each surge of plasma carrying the memory of its origin. The material accelerated along these rails will travel for tens of thousands of light years, some of it never returning, lost to the intergalactic ocean. In this sense, IC 5063 shows us how galaxies do not remain closed systems but pour themselves into the larger universe, feeding the cosmic sea with enriched gas, metals, and radiation. The rails are tributaries connecting the life of one galaxy to the broader circulation of the cosmos. The metaphor of a river also illuminates the nature of time itself. Just as water cannot be held in place but only observed as it passes, the luminous streams of IC 5063 remind us that the galaxy we see is already gone, its currents altered in the millions of years since the light left. The rails are both present and absent, like reflections on moving water, shapes that exist only because of constant motion. To watch them is to witness time flowing visibly through space, a river whose banks are starlight and whose bed is the dark fabric of the cosmos. For us, this image resonates deeply, because human life is also a river, shaped by currents both gentle and violent, carrying memory downstream, dispersing fragments of ourselves into the future. In IC 5063, the cosmic river becomes a mirror of our own, luminous for a while, turbulent in places, calm in others, always moving, always reshaping, never the same in any two moments. Thus IC 5063 is not only a galaxy of rails but a river of eternity, pouring through the night of the universe, carrying matter, energy, and memory into the infinite ocean of being. Its jets are not rigid structures but flowing songs of plasma, whispers of time itself cascading outward into the dark. Then let IC 5063 blaze before us as a flame of the universe, its rails no longer mere streams of plasma but tongues of fire licking across the body of the galaxy. The black hole at its heart becomes a cosmic forge, and the jets it launches are not cold beams but incandescent pillars of transformation. These rails resemble the flares of a sacred pyre, fire that destroys, but also fire that purifies, illuminates, and renews. Where the rails pass through the interstellar medium, they ignite clouds of gas as if setting kindling alight. Shock waves act like sparks, raising temperatures to millions of degrees, forcing atoms to glow, crack, and recombine. The gas that once lay dormant is awakened, stirred into luminous flame, its structure broken so that new forms may emerge. Just as earthly fire clears forests only to prepare them for new growth, the flame of IC 5063 burns paths of destruction that may one day blossom with clusters of stars. But this is not fire confined to wood or air, it is fire on a galactic scale, fueled by gravity itself. It consumes no oxygen, yet it breathes through the dance of particles, magnetic fields, and relativistic speeds. Its colors are not red and yellow alone but violet, blue, and invisible X-rays, tongues of flame that stretch for thousands of light-years. This is fire as the ancients imagined it, the primal element, the divine spark from which matter and spirit alike emerge. The rails thus become torches held aloft in the darkness, illuminating the galaxy like lanterns in a vast night. They remind us that fire is both danger and sanctuary, it destroys homes, yet it was the first hearth for human beings. In the same way, the rails of IC 5063 are terrible in power, yet they keep alive the larger cycle of cosmic life, ensuring that the galaxy will not stagnate but continue to change, to breathe, to renew. For us, watching from across millions of years, the galaxy's flame becomes a mirror of the fire within ourselves. Our neurons crackle with electrical sparks, our hearts beat with thermal rhythm, our civilizations glow with the fire of ideas and suns. The rails in IC 5063 show us that fire is not only a phenomenon of Earth but a universal language, a way the cosmos speaks of transformation, of endings that are beginnings, of purification through intensity. Thus IC 5063 is revealed as a galactic conflagration, not of ruin but of transmutation. Its rails are the tongues of a sacred cosmic fire, burning away the old, tempering the new, and riding light across the sky as though the universe itself were branding its eternal flame into the fabric of time. Then let IC 5063 be felt as a pulse, not only seen in light, but sensed as rhythm, as though its rails are the arteries of a vast heart beating in the body of the cosmos. The jets that cut across the galaxy do not simply flow, they throb, surging with bursts of energy like systole and diastole, an endless circulation of plasma and matter. In this vision, the black hole is no longer only a devourer or architect, but a heart itself, hidden in the chest of the galaxy, sending out pulses that carry vitality into its limbs. The rails become arteries, glowing with the flow of cosmic blood. Clouds of gas are compressed into waves that resemble heartbeats, each shock front like a pulse of pressure racing outward. Between these beats, matter slows, gathers, and prepares for the next surge, as if the galaxy inhales and exhales through its rails. To observe IC 5063 is to witness the cardiogram of the universe, sharp peaks where energy bursts forth, slow valleys where silence holds, an eternal rhythm engraved into plasma. This pulse is not confined to IC 5063 alone. It resonates outward into the cosmic web, each heartbeat sending ripples into the larger structure, just as the pulse of one cell is felt in the body as a whole. The galaxy becomes part of a vaster circulation, its rails carrying matter and energy into the intergalactic medium, feeding the veins of the universe. In this sense, every galaxy is a heart, and every black hole is a pulse generator, ensuring that the cosmos is not static but alive, vibrant, and rhythmic. For us, this metaphor is profoundly intimate. Our own hearts beat within us with the same logic: contraction and release, energy carried through veins, life maintained by rhythm. To look at IC 5063 is to recognize that our bodies are not separate from the cosmos but patterned after it. The pulse of the galaxy and the pulse of a human heart are echoes of the same fundamental principle, that life, matter, and consciousness all require rhythm, all require cycles of intensity and rest. The rails, therefore, are not merely channels of energy but cosmic heartbeats written into space. They whisper that the universe itself may be alive, not as a body in the human sense, but as a vast organism whose essence is vibration, whose heartbeat is galaxies, whose breath is the expansion of spacetime. Thus IC 5063, with its rails of plasma, is revealed as one beat in the infinite pulse of eternity. A reminder that time is not a silent river but a drum, and that within every star, every atom, every thought, the same rhythm resonates, the rhythm of the cosmos remembering itself with every luminous strike. Then let IC 5063 take the form of a cosmic hourglass, suspended in the dark void, its rails of plasma no longer only jets of matter but the luminous streams of time itself, slipping grain by grain between past and future. The black hole at its center becomes the narrow waist of the hourglass, a singular point where all paths converge, where matter is drawn inward, compressed, and then expelled outward as radiant streams. Just as sand pours from one chamber to another, so too does IC 5063 pour energy from the hidden depths of its core into the vastness of its galaxy, inscribing the flow of time into glowing rails. In this vision, each filament of gas is a grain of sand illuminated mid-fall, caught in the act of transformation. Some grains are consumed, vanishing into the black hole's silence, others are scattered, flung outward as if hurled into the future. The rails, then, are the shimmering columns of falling sand, visible evidence that time in the universe is never still but always slipping, always redistributing itself from one chamber of reality to the next. IC 5063 becomes a clock that does not tick but flows, marking epochs not with hands but with rivers of plasma stretching across thousands of light-years. What makes this image profound is the double direction of the hourglass. To us, the rails look like paths outward, jets rushing away, carrying matter into the galactic body. But to the black hole, they are also paths inward, channels through which memory and matter are drawn back, recycled, and transformed. The galaxy is thus a two-way hourglass, past becoming future, creation becoming destruction, and both flowing through the same narrow gate of the singularity. The passage of time here is not linear but cyclical. When one chamber empties, the hourglass is turned, galaxies die, new ones are born, stars collapse, new stars ignite. IC 5063's rails are only one cycle of this eternal turning, one moment in the universe's endless act of inversion. What we see as destruction is simply the flipping of the glass, what we call creation is the pouring of new sand into the lower chamber. The rails are the glowing confirmation that time does not run out, it only changes direction. For us, this image is hauntingly familiar. Our own lives are hourglasses, memories flow downward into the past, while hopes pour into the future, and the narrow waist of the present is the only place where we truly exist. The rails of IC 5063, shining across the galaxy, mirror the streams of time in our own consciousness, fragile, fleeting, yet radiant in their passage. Thus IC 5063 becomes not only a galaxy but a cosmic timepiece, a reminder that the universe itself is endlessly by unseen hands. Its rails are the glowing sands of eternity, slipping between chambers of being, showing us that past and future are not separate realms but two halves of the same vessel, forever pouring into one another through the luminous waste of now. Then let IC 5063 unfold before us as a labyrinth of the universe, a maze not built of stone but of plasma, light, and shadow, where its rails become winding pathways carved through the galactic body. These glowing tracks are not straight corridors but cosmic alleys, twisting and branching, guiding matter along routes that seem predetermined yet are filled with uncertainty. The black hole at the center is both the entrance and the heart of this labyrinth, the point from which all paths begin and to which, ultimately, all paths may return. The jets, like blazing corridors, illuminate the darkness of the galactic maze. Gas clouds become wandering travelers within it, sometimes swept along the rails, sometimes caught in turbulent chambers where currents swirl like cul-de-sacs of energy. Shock fronts rise like walls, impassable boundaries redirecting the flow, while magnetic fields act as invisible fences, forcing matter to trace spirals instead of straight lines. To follow the rails of IC 5063 is to wander a labyrinth whose architecture shifts with every pulse of energy, whose pathways are written not in stone but in living, moving fire. But unlike human labyrinths, which are designed to confuse, the labyrinth of IC 5063 serves a higher order. Its complexity is purposeful. Some gas is guided outward, nourishing the circumgalactic medium, some is compressed into knots where stars will ignite, some is scattered into silence, ensuring that no one path dominates. The labyrinth is not meant to trap, but to transform. Every turn, every rail, every dead end is part of the alchemy by which chaos becomes structure. For us, this cosmic labyrinth resonates with the inner labyrinth of life and thought. We, too, wander pathways, some lit, some obscured, some leading us to apparent dead ends that later reveal themselves as hidden doors. Our choices, like gas clouds in the rails, are guided by forces we barely perceive, invisible fields, pressures, and pulses that shape our destiny. IC 5063's labyrinth mirrors our own, not a puzzle to be escaped, but a journey to be experienced, each corridor shaping the self that walks it. At a grander scale, the labyrinth becomes a symbol of the universe itself. Galaxies are its chambers, rails are its corridors, and blatant centers, mysteries at once terrifying and magnetic. To gaze at IC 5063 is to recognize that we are already inside this labyrinth, tracing our own rails of time and memory, forever seeking meaning in the glow of paths cut through the darkness. Thus IC 5063 is revealed as a labyrinth of eternity, a maze whose walls are woven from plasma, whose corridors are written in light, whose center is the silence of the black hole. Its rails are not traps but teachings, guiding matter, stars, and minds alike through the dark, toward the understanding that every labyrinth, no matter how complex, is part of a greater pattern. Then let IC 5063 come to rest not only as a labyrinth or a flame, but as a vessel, a cosmic ship sailing through the ocean of eternity. Its rails, those luminous jet streams of plasma, become glowing trajectories drawn across the dark, like the wake of a ship upon infinite waters. The black hole at its core is the hidden engine, unseen yet relentless, propelling the galaxy forward with its pulses of energy, guiding its course across the tides of spacetime. Every burst of plasma is both propulsion and song, every glowing filament a navigational line etched upon the starry sea. The galaxy moves not alone, but as part of a great armada of worlds, each one tracing its own radiant wake across the fabric of the universe. And IC 5063, with its fiery rails, sails as a vessel of memory and transformation, carrying the remnants of past stars, scattering the seeds of future stars, and inscribing its passage into the eternal waters of the cosmos. For us, watching from a distant shore of time, the galaxy's rails are both map and message. They remind us that we, too, are voyagers on a vessel, our planet a ship of fragile light crossing the same dark ocean. The paths of IC 5063 whisper that there are no fixed harbors, only luminous routes drawn and redrawn, as the great voyage of the universe continues without end. So the galaxy stands as both monument and motion, a cathedral, a garden, a river, a flame, a labyrinth, and at last, a ship. Its rails are not just scars of energy but the glowing handwriting of existence itself, proof that the cosmos is alive in rhythm, in memory, in creation. To look upon IC 5063 is to see the universe revealing its eternal truth, that every path, no matter how violent or fleeting, becomes a luminous thread in the infinite tapestry of being. And when the rails fade, their memory will remain, woven into stars, etched into space, carried forward like light across the endless sea. IC 5063 sails on, and with it, so do we. Gas clouds, composed mainly of hydrogen, helium, and fine dust grains, float through interstellar space as immense, cold reservoirs of raw cosmic material. Within these vast and often irregular formations, hydrogen atoms, mostly in molecular form, drift in low densities, their thermal energy so minimal that the gas can cool to just a few tens of kelvins. Microscopic dust particles, made of silicates, carbon compounds, and ices, mingle with the gas, scattering and absorbing starlight, giving these clouds their often opaque, shadowy appearance when seen against brighter backgrounds. Ultraviolet radiation from nearby massive stars can ionize regions of the gas, causing them to glow with vivid emission colors, as in the Orion Nebula, where newborn stars carve out cavities with their intense stellar winds. Gravity acts subtly over millennia, pulling denser pockets of the cloud inward, compressing them until nuclear fusion ignites and new stars emerge, wrapped in cocoon-like envelopes of gas and dust. Shock waves from supernovae, stellar winds, and galactic rotation continually reshape these clouds, triggering new cycles of collapse and dispersal, making them dynamic engines of galactic evolution. Observations with radio telescopes, particularly at the 21-centimeter hydrogen line, allow astronomers to map the distribution and velocity of neutral hydrogen across entire galaxies, revealing how these gas clouds trace spiral arms and respond to gravitational perturbations. Molecular regions, where hydrogen exists as H2, are studied using millimeter and submillimeter wavelengths, most famously through the rotational transitions of carbon monoxide, CO, which serves as a proxy for otherwise invisible molecular hydrogen. Data from observatories like ALMA have shown that these molecular clouds are not uniform but are structured hierarchically into filaments, clumps, and dense cores, each stage reflecting different physical conditions and timescales in the star formation process. Infrared imaging from missions such as Spitzer and Herschel has revealed the thermal glow of dust grains heated to just a few tens of kelvins, offering insight into the interplay between radiation fields and cloud chemistry. These studies have uncovered how dust acts not only as a coolant by radiating away heat, but also as a catalyst for forming molecules on its surfaces, including water and organic compounds. Spectroscopic surveys have identified complex organic molecules, methanol, formamide, even precursors to amino acids, forming within these cold environments, hinting at the prebiotic potential of interstellar chemistry. In the Orion Nebula, high-resolution spectroscopy has mapped supersonic flows and turbulence within ionized regions, providing a laboratory for studying feedback mechanisms where radiation pressure and stellar winds regulate the efficiency of star formation. Magnetohydrodynamic simulations have shown that magnetic fields, though often subtle compared to gravity, can thread through clouds and channel material along preferred directions, influencing fragmentation and the mass distribution of newborn stars. Studies using the Atacama Pathfinder experiment, APEX, and the Green Bank telescope have traced deuterium fractionation within cold cores, a process that can only occur at extremely low temperatures, giving astronomers a chemical clock for the earliest stages of collapse. Even within quiescent clouds that appear dark in optical light, sensitive surveys in far-infrared and submillimeter bands reveal faint thermal emission, indicating that these regions are not static voids but evolving incubators, slowly accreting material from the surrounding interstellar medium. Over millions of years, the balance between gravitational collapse, turbulence, magnetic support, and external shocks determines whether a cloud will fragment into a cluster of stars, form a few massive suns, or disperse back into the galaxy without significant star formation. Space-based observatories like the James Webb Space Telescope, JWST, have begun to resolve these gas clouds at unprecedented scales, capturing the interplay of dust absorption, molecular emission, and scattered starlight in fine detail. By analyzing mid-infrared spectra, JWST can detect polycyclic aromatic hydrocarbons, PAHs, complex carbon-based molecules that form on dust-grained surfaces and fluoresce under ultraviolet radiation. These PAHs not only influence the thermal balance of the gas but also act as key intermediates in the transition from simple to complex interstellar chemistry. In regions like the Orion Bar, a sharp interface where intense UV light meets dense molecular material, JWST observations reveal chemical gradients just tens of astronomical units wide, allowing scientists to study photodissociation regions, PDRs, where molecules are broken apart and reformed in real time. At larger scales, surveys by the Sloan Digital Sky Survey, SDSS, and Gaia have shown how the distribution of gas clouds correlates with galactic structure, mapping out how spiral density waves compress interstellar matter into massive molecular complexes. These complexes, often spanning hundreds of light-years and containing millions of solar masses of material, of stellar associations and clusters. Within them, feedback from newly formed O and B-type stars, through ionizing radiation, stellar winds, and supernova explosions, drives expanding shells and bubbles, which in turn can compress surrounding gas and ignite the next generation of star formation, a process known as triggered star formation. From a theoretical perspective, advances in high-resolution numerical simulations have shed light on how turbulence shapes these clouds. Supersonic turbulence can create transient density enhancements that collapse under gravity, while simultaneously preventing global collapse by redistributing kinetic energy. Models that incorporate both magnetohydrodynamics and radiative transfer now reproduce many observed features of real clouds, including the filamentary networks mapped by ESA's Herschel Space Observatory. Interestingly, these simulations suggest that magnetic fields can act as a kind of scaffolding, slowing down gravitational collapse and affecting the orientation of protostellar disks. Chemical evolution within clouds is another active area of research. As dust grains accumulate icy mantles composed of water, ammonia, methanol, and carbon dioxide, cosmic rays penetrate the cloud and trigger chemical reactions within the ice, producing more complex organics. Laboratory Earth, simulating interstellar, have shown that such processes can yield amino acids and nucleobases when the ice is warmed, suggesting that the seeds of life might be sown long before planets even form. Observations of young protostellar systems have detected these prebiotic molecules in warm regions where ices have sublimated, supporting the idea that molecular clouds are not just stellar nurseries but also the chemical cradles of planetary systems. On cosmic timescales, molecular clouds are transient entities. Stellar feedback and differential rotation disperse them within tens of millions of years, recycling their material back into the diffuse interstellar medium. Yet in that brief lifespan, they shape the stellar demographics of galaxies, influence the interstellar radiation field, and participate in the ongoing cycle of matter from gas to star and back to gas. Studying them not only reveals the mechanics of star birth but also connects to the grander picture of galaxy evolution and the cosmic flow of matter through time. Some of the most detailed insights into gas cloud structure have come from combining multi-wavelength datasets, each revealing a different layer of the interstellar environment. Radio observations trace cold, neutral hydrogen, millimeter and submillimeter arrays like ALMA and NOMA map molecular emission lines, infrared telescopes reveal warm dust and embedded protostars, and X-ray observatories detect hot plasma from recent supernova activity interacting with cloud edges. This layered approach allows astronomers to reconstruct the full life cycle of a cloud, from its initial assembly out of diffuse gas streams to its eventual dispersal. Large-scale surveys, such as the Galactic Ring Survey, have shown that the Milky Way's molecular gas is concentrated in a narrow band along the spiral arms, where orbiting clouds repeatedly encounter density waves that compress them and set off bursts of star formation. Within these arms, the clouds are not isolated objects but parts of massive, interconnected complexes, sometimes referred to as giant molecular filaments, that can extend for hundreds of light years. These filaments often align with magnetic field lines, as measured by polarized emission from dust grains, indicating that magnetism plays a role in their stability and orientation. In regions like the Orion molecular cloud complex, high-resolution mapping hierarchy of structure elements breaking into elongated clumps, which in turn fragment into dense cores. Harbor protostars in different stages of development, from deeply Euro objects still accreting material, to more evolved Class II stars with cirques. Outflows from these young stars, seen as bipolar jets in optical and infrared images, inject momentum back into the cloud, carving cavities and stirring turbulence. These feedback processes not only shape the length but also influence which neighboring cores will collapse next, creating a spatial and star birth. Recent advancements in astrochemistry have standing of how these clouds evolve chemically over time. Observations of isotopic ratios, such as 13C/12C or D/ help reconstruct the cloud's formation history and the conditions under which different molecules formed. Laboratory spectroscopy, combined with quantum chemical modeling, has enabled the identification of molecules in space that were previously unrecognizable due to overlapping spectral lines. Molecules, like glycolaldehyde and formamide, are biologically significant, hinting at a continuity between interstellar chemistry and the ingredients for life on planets. On a galactic, the role of gas clouds extends beyond just making stars. They act as regulators in the barygalaxies, locking up cold gas during star formation bursts and releasing it back through feedback processes. In starburst galaxies and during major mergers, this cycle is accelerated, producing colossal winds that can eject enriched material into the circumgalactic medium, seeding future generations of stars in other regions. The evolution of gas clouds can have far-reaching consequences in the neighborhood. Cushions are now incorporating the physics of gas clouds into models that span from the sub-astronomical unit scale, where dust and stick, to kiloparsec scales encompassing entire galactic disks. Dynamics transfer, and self-gravity with the chemistry of hundreds of molecular species, allowing researchers to predict not just where stars will form, but also how the initial mass function, IMF, of those stars might change depending on the cloud's environment. For instance, simulations of high-pressure regions, like those found in interacting galaxies, indicate that massive stars become more common, producing stronger feedback and altering the galaxy's evolutionary path. Observationally, high-angular resolution data from ALMA has begun resolving individual protostellar disks in distant star-forming regions, revealing spiral density waves within them, potential precursors to planet formation. The presence of such structures so early in the collapse process suggests that the link between gas clouds and planetary systems is even more direct than previously thought. Disk chemistry surveys show that many of the molecules formed in the parent cloud survive into the disk phase, meaning that the volatile inventory of a future planetary system is, in large part, inherited from the original molecular cloud. In extreme astrophysical environments, such as near the centers of galaxies, gas clouds face additional forces. Tidal shearing from the supermassive black hole's gravity, intense radiation fields, and fast-moving winds from active galactic nuclei can disrupt or compress clouds depending on their trajectory and density. In some cases, observations from the Very Large Telescope, VLT, and Keck have captured clouds plunging toward a galactic center, stretching into streamers before either being torn apart or triggering bursts of star formation in the dense, high-pressure environment. This phenomenon has been observed in the Milky Way's central molecular zone, where gas densities and temperatures far exceed those in typical spiral arm clouds. Astrophysicists are also exploring how turbulence within gas clouds might set the stage for exotic astrophysical events. Dense stellar clusters born in these regions can host massive binary systems that eventually merge into black holes or neutron stars, producing gravitational waves. The recent synergy between LIGO/Virgo detections and star formation models has highlighted the possibility that the environments within certain giant molecular clouds, rich in massive stars and gravitational interactions, could be prime factories for the progenitors of these mergers. Thus, a cloud's internal dynamics can, billions of years later, echo across the universe as ripples in spacetime. Even at the microscopic level, the physics of dust grains in gas clouds ties into the grand cosmic narrative. Experiments aboard the International Space Station and in microgravity drop towers have investigated how submicron particles coagulate under low-velocity collisions, forming fluffy aggregates that can evolve into planetesimals. These aggregates preserve isotopic signatures and molecular coatings from their time in the cloud, effectively becoming time capsules that record conditions from before the birth of their star. When meteorites containing such preserved grains are found on Earth, they allow scientists to directly sample matter that predates the Sun itself. Modern research on gas clouds is increasingly powered by machine learning and artificial intelligence, which can sift through petabytes of multi-wavelength survey data to uncover patterns too complex for the human eye. AI-driven algorithms are now classifying cloud morphologies, identifying previously unnoticed filamentary structures, and even predicting which regions are most likely to undergo gravitational collapse. In large projects like the Milky Way Project and Zooniverse citizen science platforms, volunteers help trace bubble edges, filaments, and dark nebulae in infrared images, creating training datasets for neural networks that later automate the search across the entire sky. Three-dimensional dust mapping has also made a major leap forward. By combining stellar photometry and spectroscopy from Gaia, Pan-STARRS, and Apogee, astronomers reconstruct the distribution of dust clouds in the Milky Way with parsec-scale resolution. This 3D view reveals the true shapes and orientations of massive gas complexes, showing how they connect into the bones of the galaxy, long, thin filaments aligned with spiral structure. Such mapping also helps refine extinction corrections for distant objects, improving measurements of cosmic distances and the intrinsic properties of stars. Spectral analysis techniques have evolved to capture every nuance of cloud chemistry. High-resolution spectrographs on facilities like the Very Large Array, VLA, can resolve narrow molecular lines that indicate not just temperature and density, but also turbulent velocity dispersion and the presence of shocks. In some cases, astronomers detect masers, naturally occurring cosmic lasers, emitted by molecules such as water or methanol, which serve as pinpoint beacons to trace gas motion with extraordinary precision. These masers can even measure trigonometric parallaxes to star-forming regions thousands of light-years away, anchoring the scale of the galaxy. The next generation of telescopes will further transform our understanding of gas clouds. The Square Kilometre Array, SKA, once operational, will map neutral hydrogen across billions of light-years, allowing scientists to track how gas clouds form and evolve in galaxies throughout cosmic history. Combined with JWST's ability to peer into dense, dust-shrouded nurseries, this will create an unprecedented bridge between the earliest star-forming clouds after the Big Bang and the present-day interstellar medium. Interestingly, gas cloud studies are also informing planetary science in unexpected ways. Observations of protoplanetary disks reveal that much of the isotopic composition of planets, ratios of oxygen, nitrogen, and carbon, can be traced directly back to the cold chemistry in the parent cloud. This means that the fate of a planet's atmosphere, climate, and even potential habitability may be partially determined before its star is even born. The chemical fingerprint of a molecular cloud could thus echo in the biosphere of a world billions of years later. Cosmic ray interactions play a surprisingly influential role in the life cycle of gas clouds. These high-energy particles, accelerated by supernova remnants and active galactic nuclei, penetrate deep into molecular clouds, ionizing atoms and molecules even in regions completely shielded from starlight. This ionization initiates chemical reaction pathways that would otherwise be impossible at the frigid temperatures of deep cloud interiors, leading to the formation of complex molecules, including prebiotic species. At the same time, the extra ionization couples the gas more strongly to magnetic fields, subtly affecting the rate at which the cloud can collapse. Interstellar shocks, generated by supernova explosions, stellar winds, or large-scale collisions between gas flows, can either trigger or quench star formation. When a shock compresses a cloud beyond a critical threshold, it can initiate rapid gravitational collapse, creating bursts of star formation. Conversely, if the shock is too strong, it can heat and disperse the gas, halting the process entirely. High-resolution observations from instruments like SOFIA and ALMA have revealed shock-induced signatures in spectral line broadening, chemical tracers like silicon monoxide, CO, and localized heating in the mid-infrared. These observations confirm that shocks are both sculptors and destroyers, driving the chaotic beauty of cloud morphologies. Large-scale galactic flows also reshape the distribution of gas clouds. Spiral arm density waves gather diffuse gas into massive complexes, while galactic bars can funnel material toward the central regions, feeding intense starburst activity or even the accretion disks of supermassive black holes. In interacting galaxies, such as the antennae, tidal forces rip apart clouds, stretching them into long filaments where new stars are born in spectacular numbers. Simulations of such environments show that the interplay of gravity, turbulence, and feedback in these high-pressure conditions can lead to star formation efficiencies far exceeding those in calmer galactic regions. On even larger scales, the circumgalactic medium, CGM, acts as a reservoir that can feed galaxies with fresh gas and receive enriched material from galactic outflows. Observations with the Hubble Space Telescope's Cosmic Origin spectrograph have detected cold gas clouds within the CGM, suggesting that molecular cloud formation is not limited to galactic disks. These clouds may rain back down over millions of years, sustaining star formation long after the galaxy's initial gas supply has been depleted. The life and death of gas clouds is thus part of a vast feedback loop. Cosmic inflows create them, stellar processes transform them, and galactic dynamics disperse or recycle them. Each stage leaves chemical and structural imprints that, with modern observational tools, can be traced from the smallest dust grain to the largest cosmic filament. In this way, the study of gas clouds is not just about understanding stellar nurseries, it is about piecing together the entire machinery of cosmic evolution. The earliest gas clouds, forming within a few 100 million years after the Big Bang, were profoundly different from the molecular clouds we observe in the modern universe. Composed almost entirely of hydrogen and helium left over from primordial nucleosynthesis, they lacked the heavier elements, carbon, oxygen, silicon, and beyond, that today's clouds inherit from countless generations of supernovae. Without these metals and the dust grains they form, the cooling processes inside primordial clouds were far less efficient. Instead of radiating away heat through molecular lines from CO or dust thermal emission, these first clouds relied primarily on molecular hydrogen, H2, and, to a lesser extent, deuterium hydride, HD, to lose energy. This meant they could only cool to temperatures of a few hundred kelvins, significantly warmer than modern star-forming clouds, which often reach just 10 to 20 K in their densest regions. This higher temperature floor had a profound consequence: the gene's mass, the minimum mass required for a cloud to collapse under its own gravity, was much larger. As a result, the very first stars, known as population 3 stars, were likely extremely massive, often exceeding tens or even hundreds of solar masses. Their intense ultraviolet radiation rapidly ionized their surroundings, and their short lifespans ended in hyperenergetic supernovae or even direct collapse into black holes. These explosive deaths seeded the surrounding medium with the first heavy elements, creating the chemical diversity necessary for dust grains, water molecules, and complex organics to form in later generations of clouds. Simulations of this epoch, run on some of the world's largest supercomputers, suggest that these early gas clouds often formed in the densest knots of the cosmic web, where filaments of dark matter gravitationally funneled baryonic gas together. Observations of extremely distant galaxies with JWST are beginning to reveal possible signatures of this process: compact, intensely luminous starburst regions that may be analogues of primordial clouds undergoing their first episodes of star formation. In some cases, gravitational lensing magnifies these young systems enough for astronomers to detect spectral hints of nearly pristine gas, untouched by heavy element enrichment. The transition from primordial to metal-enriched clouds marked a turning point in cosmic history. Once even trace amounts of carbon and oxygen were present, cooling became far more efficient. Dust grains formed, catalyzing the production of molecular hydrogen and shielding interiors from destructive radiation. This ushered in an era where lower-mass stars could form, many of which, unlike the massive population 3 giants, would survive for billions of years, some still shining today as ancient red dwarfs in the halos of galaxies. Thus, the evolution of gas clouds over cosmic time is inseparable from the evolution of the universe itself, from the hot, metal-free clouds that birthed the first stars, to the richly structured, chemically complex molecular nurseries we see in the Milky Way today. Studying them is like reading the universe's autobiography, page by page, molecule by molecule, from the first whispers of starlight to the bustling stellar cities of the present epoch. Future observatories are poised to transform our understanding of those earliest gas clouds, bringing the cosmic dawn into sharper focus than ever before. The James Webb Space Telescope has already provided tantalizing glimpses of galaxies existing just 300 to 400 million years after the Big Bang, but upcoming instruments will go deeper, wider, and with greater spectral precision. The Nancy Grace Roman Space Telescope, scheduled for launch in the coming years, will conduct wide-field near-infrared surveys capable of uncovering vast populations of faint, early galaxies. By statistically mapping their distribution and luminosity, astronomers will infer how the first gas clouds clustered and evolved within the cosmic web. Complementing Roman's wide view, the extremely large telescope, ELT, in Chile will offer unparalleled spatial and spectral resolution for individual high-redshift systems. With its 39-meter mirror and adaptive optics, ELT will be able to dissect the light from tiny star-forming regions inside early galaxies, measuring the metallicity and kinematics of gas clouds on scales of just a few parsecs. This will directly test models of population 3 star formation by identifying pockets of nearly pristine gas amid enriched regions, revealing where the first supernovae had yet to leave their mark. Radio astronomy will also play a decisive role. The Square Kilometre Array, SKA, will map the faint 21 cm hydrogen signal from the so-called cosmic dark ages and epoch of reionization. By detecting the fluctuations in this signal over time, SKA will create a three-dimensional picture of how the first gas clouds condensed, ignited, and carved out ionized bubbles in the neutral intergalactic medium. Such observations will bridge the gap between theoretical simulations and direct detections, showing exactly how small, cold clouds assembled into the earliest galaxies. On the simulation front, advances in exascale computing will allow researchers to model these primordial clouds with unprecedented physical realism, including detailed treatments of radiation hydrodynamics, molecular chemistry, and feedback from the first massive stars. These models will guide observations by predicting the spectral fingerprints of primordial clouds, from hydrogen recombination lines to subtle signatures of HD cooling. They may even help explain anomalies in current JWST data, such as unexpectedly massive early galaxies, by revealing new pathways for rapid gas collapse in the early universe. Looking even further ahead, next-generation space telescopes like LUVOIR or HabEx could extend ultraviolet spectroscopy into the realm of the first billion years, tracing how heavy elements spread through the cosmos and transformed gas clouds from pristine hydrogen, helium reservoirs into the chemically rich nurseries capable of making rocky planets and life-bearing systems. In doing so, they would not only illuminate the birth of the first stars, but also set the stage for understanding the ultimate origin of worlds like our own. Gas clouds are deeply embedded in the grand cosmic cycle of matter, linking the smallest scales of molecular chemistry to the largest structures in the universe. Over billions of years, they have acted as both the product and the driver of